Welcome back to Third Phase of Moon. Blake Cousins here. We've got a special report. Have you heard of anti-gravity? Well, apparently it's possible that our own technology, people, scientists, could prove that it actually exists. Louise Riofrio has a theory that she's going to discuss right here at Third Phase Moon, and we have Alex with us who's very interested in the subject matter. Louisa, thanks for joining us right here at Third Phase Moon. Can you give us a little background on who you are and what this theory is about?
Oh, hi, Blake. Yes, I'm Louise Riofrio. I studied physics and astronomy at universities in California. And after that, I worked as a scientist at NASA Johnson Space Center in Houston, studying the moon, where I did experiments with Apollo moon rocks that no one had touched in 45 years. And more recently, I've been working on my home in the Big Island of Hawaii on a project to place telescopes on the moon. And today I'm in Alaska.
Incredible. Even Alex is from the Big Island. Alex, can you give us a little background on yourself?
Yeah, I live on a big island. Well, I live in San Francisco, but because we're staying on the Big Island, we've been here for about a year. I have a degree in astrophysics from Hunter College in New York City, CCNY. And I'm really interested in what you're doing. And I met Blake and Brian a couple of weeks ago, and they told me about you, and I'm thinking maybe you have something.
So let's yeah, that's absolutely why we're doing this meeting right now. We got two collective minds going after the possibility of anti-gravity. So let's start it up with Louise. Louise, tell us, you approached me about 2 months ago. You said you had a theory and an actual prototype that proves that anti-gravity exists. Could you tell us about this, Louise?
Oh, I'd love to tell you. Oh, this is the most exciting thing I've ever worked on. Now, last year I told you about my equations for the universe that predicted, among other things, that the speed of light has changed, which affects time and many other things. But I've done some further math, and we have two big theories of the past 100 years. Quantum mechanics, which covers the microscopic world, and general relativity, which is Einstein's theory of gravity. Now, for more than a century, people have tried to combine them into one theory, but I was able to actually do it, prove that gravity itself is quantized. It's quantum mechanics and gravity aren't separate theories, they're part of one bigger theory. And furthermore, I developed an experiment. Oh, I wish I could show it to you today, but I didn't bring it to Alaska. A device no larger than a child's marble that allows us to test it. In fact, within this device, and we don't have time to describe how it works, there is no gravity. This is something that any classroom or any laboratory could build, that we one day hope to put on board the space station to test it in the microgravity. And this will be probably the biggest advance in gravity in the past 100 years. All those things you see in your videos of anti-gravity devices or flying machines, this could be possible, just as our understanding of quantum mechanics allowed us to build things like transistors and lasers. This will allow scientists and engineers to someday understand and even control gravity and make all those things in your videos come true. And that's what I've been working on. It's very exciting.
So Louise, you say there's this device the size of a marble. Is it here on the Big Island of Hawaii?
Oh yes, I'm afraid it's in my lab on the Big Island. I'm afraid I didn't bring a model of it here to Alaska, but it's easy to miss.
So how does it work?
Well, it looks just like a marble.
How does it work?
Well, that's actually
First of all,
complicated.
Okay, uncomplicated. What is it? What is it made out of? How big is it? What are the forces that act on it? What does it do? If I saw it right now, what would it do?
Well, it's made out of a clear polycarbonate, and it's 1.8 centimeters in diameter. Now, how exactly it works, well, that would be like describing an integrated circuit to Jules Verne. I could talk you through it, but it would take days. But within it, we place two test weights. Now, according to all the laws of gravity, the two test weights should attract each other, but they don't, because within the experiment, the normal laws of gravity don't apply. Now, this is a tiny experiment. I made it small, so my astronaut friends will someday be able to take it on board the space station and test it there. But we could always scale it up.
So you have something the size of a marble. I'm just asking questions. So you have something the size of a marble that has some weights inside it, and you still haven't said what it does, or what would I see if you place this marble in front of me? Would it levitate? What actually are you saying? So far, I've got a marble with two little weights in it. That's what I've got.
Yes, and our laws of gravity say that all masses attract each other.
Maybe.
Yeah, I mean, as Galileo showed on the Leaning Tower.
So I'm here to listen, so I'm not here to argue with you. But yeah, they do attract you, but basically Einstein says that it's a curvature of space. So I don't want to get into that. I'm not getting into that. Well, basically, my question, my reason to be here is to understand if you're saying that, and by the way, Einstein predicts negative gravity, so okay, fine. If I put this thing on a table, what I'm hearing Brian say is that you can make it levitate. So I'm trying to figure out how it is that works.
Oh, I'm afraid. We might have been misquoted. The device can't actually levitate itself.
Oh, okay, fine. What does it do? Then even better. So as a concerned questioner that wants this thing to exist, what does it do?
Oh, well, it's a test device. Within it, we place two small weights. Now, as everyone knows, Galileo showed that two weights dropped from the Leaning Tower will both fall towards the Earth at the same rate, because they're both attracted to Earth's mass. Now the laws of gravity say that all objects with mass attract each other. Now we place two weights within the marble. According to Einstein's theory and even Newton's theory, they should attract each other, but they do not. Because within the marble, there's no gravity, and the laws of gravity that we know don't apply.
Well, that's what I mean. How did you make the laws of gravity not apply inside the marble? What is, okay, I'll even give you that you made the laws of, I'm confused.
All right, well, this relates to something I told Blake about a year ago. I came up with equations describing the origin and evolution of the universe. And they're incredibly simple. I guess the most important one, if I wrote it on a blackboard, would look like M equals R equals T, which is incredibly simple, but M is mass, R is space, and T is time. And this applied to the universe, it means that the universe has a size and an age and even a finite mass that is equal in terms of what are called the Planck units, microscopic units that were pioneered by Max Planck. Now, this simple equation, which apparently hadn't been discovered before, explains everything about the big universe that you wanted to know but were afraid to ask. How big it is, how fast it expands, whether it will stop expanding, but it also applies to the microscopic world and tells us that gravity itself is quantized. That quantum mechanics applies to gravity. And linking gravity with quantum mechanics is something that theorists have tried to do for over a century. And this time, we can not only show it, but we can test it.
Okay, so you, I'm sorry, go ahead.
Alex, this is the whole point. We want to test this device of yours. It's the size of a marble. There's not really much
but I'm sorry, but I still don't know what it does.
That's what I was going to get at. Like, there's no practicality to anything that's the size of a marble. Are you saying if you expanded this into a bigger prototype, you could actually, you know, transport human cargo if this was put up on a bigger scale? Do you have a patent on this, Louise?
Well, you'll read all about it. The scientific paper describing it is going through peer review right now, and will shortly be published, which describes, you know, how this works and also how you could reproduce it in your laboratory or even in a classroom.
But just to my small brain, what is it that it does? You have it. Okay. So theory aside, your theory aside, I don't understand what you will show, how you will determine that there's no gravity between these two objects inside your little sphere. But let's say, well, okay, how will you show that? How did you show it? Is this a theory? Did you actually measure the forces between these two objects inside the sphere?
Yes, and we can actually predict them just from the well-known laws of gravity. Now, according to those laws of gravity, the two weights should attract each other because they would both bend space-time.
You're using Newtonian or the Einsteinian?
Oh, both Newton's and Einstein's gravity say that the two weights should attract each other.
Yeah, but for different reasons.
Yes. In Newton's law, it's action at a distance. Einstein's law expands upon it and says that, you know, all masses cause curvature of space-time, which attracts other masses.
No, that's not what he says. It's curvature of space-time makes them form into the space-time distortion.
Oh yes, that's another way of putting it. My way, what you're just saying is alternative facts. Okay. Oh yes.
It doesn't attract. There's no rubber band that goes out but still, there's no rubber band that goes out and pulls the other thing towards you. So that's fine. But I still don't understand what your device does.
Oh, it's an experiment according to those laws of gravity.
So let's make it the size of my house. What does it do?
Well, all houses get dust. You know, when you dust out your house, the dust falls to the floor.
Make your marble the size of the house.
Let her explain. Wow. Let her explain quickly. Go ahead, Louise.
Well, all houses gather dust. When you dust out the house, the dust grains fall towards the floor because they're attracted by the Earth's mass, but they do not attract each other. And that's something that many people have observed, but it's a clue to a quantized nature of gravity. Again, you know, within the marble, according to the two test weights, according to those laws of gravity, both Newton and Einstein's should attract each other and eventually merge. But in tests, they don't, because their gravitational force is quantized.
Louise, when you say that
and this is something that anyone can test.
Yeah, you say this could be done in a classroom for students, but again, Alex is saying, what are we going to see? What are the students going to see with their naked eye? What kind of project would you bring to a classroom if you really aren't seeing any kind of, you know, reaction? Is it visible? Is this thing going to levitate? Why would the kids be interested in it if they're not going to see anything with their own eyes?
It's a great question. You said that the dust doesn't attract each other. Did you ever see a dust devil under your bed? Of course it attracts itself.
We get into that in the paper. The phenomenon of dust bunnies that gather in corners are caused by a combination of electrostatic and aerodynamic forces. So dust bunnies are a product of an electrostatic attraction between dust. But the experiment removes, you know, all those other factors to show. And well, we can't take our children into outer space to experience microgravity, but this shows them what a lack of gravity is like. The two weights don't attract each other.
About, is it possible to build an anti-gravity machine? What would it take? It's the size of a marble. This is on a really small scale, what you're talking about, an experiment.
Blake, I understand.
What do you understand, Alex? What do you understand? Go ahead.
So you're not, she's not, I understand. I think I understand what you're doing. So tell me that if I'm wrong. She's not proposing an experiment that does anything. What she's suggesting is that the Einsteinian view of gravity and the Newtonian view of gravity might in fact be incorrect. And the way she's trying to prove it is she's got these two tiny little weights that seem to not function the way that I guess Newton or Einstein would describe the attraction. Am I in the right direction?
Yes. Yes, you've almost got it.
Okay, so my question would be, and this is cool now, having studied physics in the 70s, and haven't really studied anything since then. I'm a software guy. What you're saying goes contrary against not so much Newtonian, but definitely Einsteinian. And it'd be nice to see a proof of that. You'll become instantly famous and get the Nobel Prize. But I'm sorry, there's no way that that's correct. There's too many experiments in Einsteinian physics. There are too many experiments in Newtonian physics that I would be very surprised, but convince me.
Once again, any classroom can do this experiment, and eventually we hope to do it on board the space station.
So the time will tell. Time will tell. It's under review, right, Louise? So when do you think, when this is under review, you put the information out, when are we going to get any feedback that your theory is possibly correct and we're going to have a device that proves it?
Oh yes, we certainly will. And well, Blake, it might not lead to anti-gravity aircraft right away, but just as our understanding of quantum mechanics has enabled scientists and engineers to create things like lasers, transistors, and integrated circuits, if we understand the quantum nature of gravity, we'll eventually be able to build those things. Just like in that movie Interstellar, where Michael Caine plays NASA's greatest scientist who struggles to try to discover quantum gravity. And finally does, which enables man to conquer the stars. Now, again, this is just an experiment, like those early experiments with quantum mechanics and the photoelectric effect. But it's a start, and this is something we can prove. And as you know from interviewing me previously, I came up with math that predicted what the speed of light is, not just what it is today, but what it was yesterday and what it is in the future. And though it's not well known, we've since proven that. And there's another experiment already going to the space station that can prove it further. So my resume prepares me for this.
Let's get into one quick question. We're just about ending this, but everybody's asking me, and people wanted to ask you because they've seen your previous episode on third phase of moon. What's your thoughts on element 115, Louise? Is it a possible element? Is it out there? Would it help in your experiment if you were able to obtain element 115?
Well, it wouldn't directly help it. However, element 115, if it can be synthesized and stabilized, would be quite dense. And having a dense mass within the experiment would prove it further. We could show that even for something very dense like element 115, the laws of gravity would not apply within the experiment.
Alex, what's your thoughts on anti-gravity in general? Do you think it's a possibility?
Well, Einstein predicts it. Dark energy supports it. It's not. When you start speaking about anti-gravity, you have to understand what gravity is, and no one really does. So anti-gravity, what is anti-gravity? But I don't see us being able to develop an anti-gravity machine until we fully understand what gravity is. And I'm concerned about what we're saying here, because why couldn't you do the experiment with two huge balls, by the way? Louis, if I hang two big balls on a string, they will attract each other. Now, what you're suggesting is that it doesn't on a small scale, and that I don't see it. So why can't I use two giant balls a millimeter away from each other to reproduce your experiment?
Well, with larger balls, well, that gets mathematical, but the experiment works better on small masses. It might be more work, to scale it up. Of course, if we could do this with big masses, we could build your anti-gravity aircraft. But I'm not going to say we're there yet. Right now, it's just a small experiment.
Okay, I don't see how even okay, I'm not going to get into it. There's too much math that we could get into that I don't see where this is going in terms of reality.
Louise, where can we see your finalized report? You've submitted it; it's under review. Do you think we could get that report? I could send it over to Alex so he could take a look at this, and we'll touch base later when the peer review goes over your theory.
Yes, once again, it's going through the peer review process that's nearly finished. It'll appear in a journal probably the last quarter of this year. I can't tell you exactly when, because things have slowed down because of the virus.
Who's peer reviewing you? What
they're over in Harvard. They're in the Journal of Cosmology. And I wanted to give you just one example of where this is going to lead. Now, if you touch your heart, all our human bodies, in fact, all life on Earth is made up of cells. All of it. And Isaac Newton's contemporary, Robert Hooke, when he looked into a microscope, saw that all life, large life, is made up of cells. But why our life is made up of cells, and why cells are the size that they are, that's something that no one's been able to figure out. You might have heard a theory involving density and surface area, but that's not been proven by experiment. This experiment shows why life is divided into cells and why they are the size that they are. And that affects, our biology and even the action of that virus that everyone's heard about. And that's something right away. It tells us why our body is made up of cells.
Yeah, there is an interesting theory that you bring up, the size of cells. Why are they this size to actually create and form matter, living organisms? It's a mystery still to this day. You know what, I want to thank you guys both for joining us. I know we're still trying to figure things out, and Alex wants to get to the truth, and he wants to know as well as we all do. And Louise, if you find out anything, this peer review, you keep in touch, let us know the results on this, and hopefully we could move on to possibly even making a device that we could actually see levitate or see it work or have some kind of function. But until then, keep in touch, Louise. I know you're over there in Alaska. When you get over here to the Big Island, I'd like to see your device, your little prototype, your experiment when you get here, and Alex is going to join us as well.
Oh, yes, Alex and Blake. I'd love to talk with you further. I'll keep you in touch. And next time on the Big Island, I'd love to visit either of you.
Yeah, I think I'm here for the duration.
All right.
We'll see on how this all plays out. Everybody, thanks for joining us today in the premiere, all the chats. Everybody's very supportive. This is a kind of an interesting little segment that we did on Third Phase, but it's a little debate, and that's what we're here for. Opinions, that's what we need, a lot of them out there. Everybody, keep your eyes on the skies, be safe. Blake Cousins, we'll see you next time.